Yes, I'm going to be talking about nothing that was advertised. So
forget about the previous title.
there you go, yeah. There's many possible jokes here. Okay, let me give you an introduction. Yeah, so let's see. So the functor we're interested in, it's going to go from schemes to topological spaces. And one person's going to be surprised about the topic of this lecture. So given a scheme, just associate the underlying topological space. So all the closed points, and then the topology is just as risky topology. So it's a risky topology, of course. And of course, given a morphism, you just get a continuous map. And so the question is, to what extent is this forgetful? And the answer, well, so it looks like the answer is a lot when you start thinking about it, because if you work over a field, so yeah, I'm going to work with typically varieties over a field, and let's suppose, just to make it easy, the field's algebraically closed, and you've got two curves, C and D over K, then of course they're homeomorphic, because they've just got the same number of points and they're closed subsets of the finite sets. So it looks like it's very forgetful. But in fact, that's not true in general. So this is, I just really love this theorem. So, by the way, my contribution to this subject is not very substantial, certainly at the moment. So this beautiful theorem, choose a color, Lieblich, Olson, and so in. So I won't state all the results they get, but I'll state the two main ones. So if suppose you X and Y are normal, projective, and now over fields K and L, so they don't even have to be the same field, which is kind of interesting. And let's assume that the characteristic of K is 0. That's an absolutely crucial assumption here. Then, and suppose that the underlying topological spaces are homeomorphic. So I'll just denote the underlying topological space by in this brackets X. So there are two cases where you can recover. One is when, let's say, the dimension of X is at least 4. It seems a bit silly, but if you think about it a little bit, once you know the dimension of one variety, you know the dimension of the other one. Then X and Y are isomorphic. Over an isomorphism of spec K and spec L. Of course, the whole point is, you don't know what the you can say the fields are isomorphic, but you could change the isomorphism. And then the other, so that's one possibility, and then if long as dimension of X is at least 2 and K is uncountable, then basically you get the same. Then you get the same conclusion that the isomorphic over an isomorphism of the fields. So the answer is not very forgetful. Not very. Okay. And then so they conjecture, I'll put the conjecture here. Do I have a blackboard here? No. Then they conjecture that, I mean, basically, if enough to assume dimension x is at least 2, and then no hypothesis on k except characteristic k is 0. So as soon as you have two homeomorphic surfaces over a field of characteristic 0, then the two surfaces are isomorphic over a field isomorphism. Any questions about that? Okay, so maybe what I should now do is, maybe I should give a little bit of motivation and then give a lot of background, because you probably haven't thought about this problem, and you're probably wondering, what's it? Yes? That is a very interesting question. Let's come back to that. Yes, that's a great question. Maybe we don't. It's not clear. Sorry. Do you need projectivity or not? Yeah. It might be yes. It's not clear. So maybe give a little bit of motivation and some related work, which I find kind of interesting. So, I mean, personally, I just find the question fascinating. It just seems kind of crazy to me that all you need to recover a variety is the Zariski topology, right? I mean, you know, we're sort of taught scheme theory. We're taught about you need functions. You need to understand structure sheaves. You know, perhaps it's better to work with the Tal topology. The Zariski topology just isn't good enough, blah, blah, blah. But in fact, everything's determined by the Zariski topology as soon as you get to surfaces, well, conjecturally. Okay, so let me give you maybe a little bit more motivation, which I think is part of what it went into for Lieblich and Max and Martin. So one obvious thing is that given a variety, one can associate various categories, let's say a category of sheaves. I mean, in various contexts and various sheaves, I mean, the classical case is Serre. And then, of course, with those hypotheses, you can often recover the variety from the category. And I guess that in some ways, this sort of theorems go some way to explaining why that's the case, because it's perhaps not quite so surprising that given the category, you can recover the topology, because I mean, the structure sheaf, given this category of sheaves, there's the structure sheaf of any subvariety, and then there's the structure sheaf of points. And really, you just somehow need to recover that structure. So I sort of, from that sort of point of view, I think these sort of theorems are quite interesting, and I think that was one of the original motivations for this theorem. And then I should also say that there's some related work, which is also quite interesting. Definitely, I should mention some work of Bogomolov and Yurichenko. Which is sort of a different flavor, but in the end, so the hypothesis and the arguments are quite similar. So the idea is it sort of comes from Alabinian geometry. And basically, you try to recover the variety from Galois theory. I don't know. There's a good person to ask about this here, certainly not me. But what's very interesting is that some of the techniques are quite similar. And there's also a very interesting, something that actually comes from their work, which I think is one of their conjectures. It's the work of Zilber, which is perhaps even more interesting. I mean, sort of this from this context, because it actually even does the case of curves. So if you have a curve and think of it embedding it inside the Jacobians somewhat sloppily. I mean, it should be the divisors of degree, line bundles of degree 1. So you think of this as being a group, abelian group, of course. Or I should say that very important here that the field is algebraically closed. Then you can recover C from the Jacobian just as a group and this embedding. And what's very interesting about this is that the techniques that just come from logic, from model theory. So, I mean, strictly speaking, just you know, I mean, okay, pick one, C, and then think of it as a torsion under this group. I mean, yeah, then it is embedded, right? Oh no! As an abelian, I forget the structure as a variety. Just the abstract, just as an abstract group, just this abelian group, and this embedded. Yeah, this. Yeah, this subset. Yes. Yeah. Rational is fine. You can recover from rational. If you tell me the image is a point, I'll tell you that it's a P1. Yeah. So there are these techniques for model theory. They're sort of related to what I'm going to talk about next. But what's so very interesting is that the techniques for model theory are so different to everything else. Any other questions? Okay, so having talked about the motivation, perhaps let me give you some background, which you'll sort of start to understand the sort of flavor of these sorts of problems. Maybe I should, maybe I'll keep that. Yes, so maybe I should say one thing. So somehow, okay. So if the theorem is true, and if the conjecture is true, then somehow you can recover everything from the topology. But still, I think it's sort of useful to sort of ask yourself the question. So given the topology, what is easy to recover and what is hard? Because you probably sort of have not thought about this problem before. So, I just make two columns. Let me just call it the visible column and the opaque column, because again, everything, in the end, you should be able to recover everything, right? So what's in the visible column? Well, not much. So, obviously, if I give you the Zariski topology, you know what the irreducible subsets are. And that's, of course, very useful, because then that gives you the dimension. So I already mentioned that, but let me just make that clear. And so now you've got the closed subsets and you have the dimension. So really what you have, then you have, well, you know what the points are, you know what the curves are, you know what the surfaces are, dot, dot, dot. And it's going to seem strange at first, but become a little bit clearer later. Then really what you have is the incidence correspondence between these things. And then one other thing you have, which is very useful, which is sort of goes back to what goes on into this theorem, you have the divisors, of course. Okay, so what's opaque, what's hard to see? Well, the thing that's probably the hardest to see is any notion of multiplicity in any sort of guise you can imagine. So, for example, the easiest sort of thing that you can't see the multiplicity, if you took a cuspidal curve, and you take its normalization, this is a homeomorphism. So you just don't see lots of singular points. You just lose them when you just look at the topology. It's sort of obvious. No, it does happen. So, yes, that's why I suppose that X and Y are normal. Yes, and then what else? So you can't see the difference between two curves crossing transversely and a curve and something that's tangent, no matter how tangent it is. You just can't, you're just not given that information. Because again, these are homeomorphic as Zariski subsets. Of course, in characteristic P, you've got Frobenius, you know, whichever, let's say absolute Frobenius, you just don't see this. This is a homeomorphism. And there are lots of inseparable maps, and none of those you see. So that's why you want to assume the characteristic is 0, because it's a much harder problem in characteristic P. And then finally, just let me point out one thing which won't come up very much today because of my hypothesis, but let me point it out. Let's suppose, for example, you had something over R. You don't see the difference between an R-valued point and a spec Rx over x squared plus 1 point, a pair of complex conjugate points. They're just, I mean, if you give yourself the whole scheme, topologically they're just the same. So what's very hard to see is any sort of notion of multiplicity, a priori, right? Also what's hard to see, what is quite important is numerical equivalence. I mean, of course, if you can't see intersection multiplicity, it's not so hard to recover numerical equivalence or linear equivalence, or just pick any property you choose. It's very hard to see it. Lifted to. Oh no. No, I am. So yeah. I mean, yeah. If you give me a homeomorphism between X and Y, it corresponds to an algebraic map. Yeah. So I mean, I mean, there is somehow a functor. It's not, you know. Yeah. Any other questions? Okay, good. So hopefully you're beginning to see where the difficulties lie. Okay, so maybe I should also give you some background, so start give you some positive results. So the first really, I just love this result. It's a classical result. I guess it's called the fundamental theorem of projective geometry. Although first I'm going to state it for vector spaces, but anyway. So if you have vector spaces, V over a field, W over a field L, and then you're given a correspondence between the lattice of subspaces of V and of L, of W, then, well, and one hypothesis, dimension of V is at least 3, then that implies that dim V is dim W. That's easy. And more importantly, K is isomorphic to L, and then under that isomorphism, that there's some linear, there's some, what it's called, I forget what it's called. It's not quite linear. It's linear over that map. And then there's a linear map over this isomorphism. Okay, so let me make an obvious thing that everybody's going to be happy with in this lecture, that this is really a result about projective geometry. Obviously, if I tell you all the subspaces, really I'm telling you about, it's not surprising it's a result of projective geometry. So really, it's enough to look at all the linear subspaces of projectivizations of these two guys. In this case, of course, then this result becomes that the dimension of the projective space is to be at least 2, and then so it's pretty obvious why I need at least hypothesis, because again, if I give you P1 and P1, there's just no way you can recover to just the lattice. All you really know is the cardinality is the same. And then where does this result really come from? Well, I'll say the sort of the low sort of key way, and then sort of point out it's a little bit harder than that. But essentially, what it is it's just basically, I mean, really, what you want to do is recover the field operations, addition and multiplication. And how do you get? Oh, one other thing. You only need to know about points and lines. In other words, you give yourself a function between the points and a function between the lines, and you just know that if a point lies on a line, then its image lies on the image line. That's all. So how do you get addition, multiplication? Well, it's just classical Greek geometry, right? If I give myself two lengths, I can just add them together, and if I give myself two numbers, I can multiply them together using, the usual pictures Greek geometrists used to write with similar triangles and stuff. Well, that's not quite right, because this is projective geometry. So you need, to rigidify a projective line, you need 3 points in it. So it's actually harder than that, but that's the basic idea. And one of the key things in this theorem is, in fact, you only really need this. I can even weaken this even more. You only really need this for an open subset. An open subset. I mean, really the key thing is the Grassmannian of lines in V. So in some sense, it's a result in birational geometry. Let me place that idea in your head. Any questions about that? Okay, good. So in fact, this thing about recovering the field is not quite so bad, because in the end, you try and get yourself a projective space, and then once you have the projective space and some sort of correspondence, then you can recover the field. So perhaps that becomes a little bit less surprising, that aspect of the whole story. Okay. Okay, so let me now describe my kind of naive approach to all of this. So I should say, I mean, he's going to be quite surprised about this, but I've had some conversations with Fangjun Ben about this. Although, I mean, there's no results to state at the moment. Okay, so we already know this for an uncountable field. Oh, I should say that there's what I should have said. The theorem has one other part about threefolds, but it's kind of hard to state. You need to make an assumption about the field. But the two very clean results to state are for the uncountable case and the case of dimension at least 4. The case of the threefolds, it's much more of an arithmetic nature. Okay, so let me give myself an uncountable field. Oh, sorry, countable field. But I mean, let me make it easy for myself for the time being. Let me just give myself Q bar, nice countable field, but plenty of countable fields you could take, something like that, algebraically closed. And of course, characteristic is 0. Hopefully by now that's clear that that's important. And also I'm going to make it easy on myself. I'm going to assume my surface. So now I'm going to work just to do the case of dimension equals 2. Because I think that's somehow the key case. I think if you can do the case of dimension 2, I think it's, I'm hoping the other cases kind of fall out from that. And so if I'm going to assume that dimension 2, let's say I have a surface S, it's projective. I'm also going to cheat a little bit. I just want to assume it's going to be smooth. Again, I don't have any results in general otherwise, and this is a nice simplifying assumption. And then, of course, my other thing will be projective. My other surface, let's call it T, is projective, normal, let's say. And let's suppose, and so I'm assuming that the two surfaces are homeomorphic. And what I'm trying to show is that, in fact, they're isomorphic over some isomorphism of the ground fields. I don't think that's important. Yeah. Is smoothness what? I see. Okay, this is an important thing. So, no, no, it's not because of again that no, not at all. Any notion of multiplicity is opaque as far as I can see. Yeah. So somehow the thing to realize is, we say that we're going to only use the Zariski topology, but I mean that is a bit of a misdirection, right? Because what I'm going to do is on this surface, I'm going to use everything I know about surfaces, and on this other surface T, I'm going to try and everything I know about surfaces. Now, in terms of singularities, of course, this I'm just assuming that T is normal, so you can have finite many singular points. But I mean, okay, I don't see those points. But maybe yes, I do, because under my homeomorphism, I just get finite points here. So I'm just going to avoid those points in all my constructions. And then at the end, I'm going to, I mean, anyway, I don't have that many results at the moment. And once we get there, that'll be sort of obvious. So what's hard is to get going at all. I mean, what's hard is to prove anything. So once you get going, I mean, somehow basically what you want to do is exactly that. You want to move things from the opaque into the visible, right? You want to make conclusions. And it's the beginning it's so hard. Once you get going, it's not so bad. Okay, so let me make some observations. Okay, so observation number 1, which is going to seem kind of silly at the beginning, but it's actually quite useful. It is enough to show given a homeomorphism from S to T, there exists phi, a birational map from S to T, which agrees with F on an open set. And this is sort of obvious, everybody sort of knows this, because you take a point P in S that lies in the indeterminacy locus of phi, then there will be some curve. I've got to run out of symbols here. Let's call the curve F on T. And so what you can do is sort of obvious. You can write down two curves on T that don't intersect on F. Let's call those ones D1, D2. And of course, then on, maybe I haven't made this very clear, then on S they intersect, which contradicts the fact I have a homeomorphism, right? This is a somewhat sort of strange, sort of pedantic way to sort of say this, but I actually want to avoid using the graph, because let me point out one other thing that's kind of, it's just a sort of consequence of the fact that if you have an point of indeterminacy, on one side, on the other side, you've basically, your indeterminacy locus is a curve. I just want to avoid using the graph, because let me point out another kind of annoying fact, which is really the whole point of the story. The product topology is not the same as the product in category schemes, right? So that's the whole point. Because otherwise, then, if you can't recover a curve, you couldn't recover a surface either, right? But that's, and the other thing about that lattice of subgroups and points and lines. Hopefully now it's a bit more clearer what's so important about incidence. Okay, so it's basically a birational question. So let's just apply Mori theory. Let's think about this from the point of view of Mori theory. Okay, so suppose S is not minimal, right? So then there exists E inside S a -1 curve. Okay, well on T, I'd see a curve F. But I don't know anything about this curve. I don't know its P1, and I don't know, more importantly, that it has negative self-intersection. Okay, but what do I know? Well, I know I have a -1 curve, so I can contract E down to a point. Okay, and then this is a projective surface. So here I can find lots of curves that don't pass through P prime. In other words, on S, I can find lots of curves that don't meet E. And that's a purely topological property. So now on this surface T, I see a curve F, and I see lots of curves D disjoint from F. Okay, now I say Hodge index theorem. And I say, what do I get? Well, there's various possibilities, right? Could F squared be positive? Well, if F squared is positive, then D squared is negative. Okay, then you worry about that for a little bit, but then you realize you can write down lots and lots of curves here, disjoint from F. So there are lots and lots of curves disjoint from E. So there are lots and lots of curves here disjoint from F. So it must be the case, therefore, if you think about it a little bit, you can construct from, it couldn't be that all of those curves are disjoint from F and F squared be positive, because then, if you took enough more of the curves than the Picard number, for example, all of those curves would be contractible, for example. And that's just nonsense. So that's impossible. Okay, could F squared be equal 0? Well, in that case, F and D would be proportional. Well, and I mean, having ruled out the possibility that d squared is negative. And so d squared is f squared equals 0. Well, now take another curve in S, then I'd have another curve d prime. It's also disjoint from f. If it's, again, self-intersection 0, then again it would be proportional to f and therefore proportional to d, and that's nonsense, because again I could just choose them to intersect each other. So eventually, the only possibility is that f squared is less than 0. Process of elimination. And so then I can contract this curve down on T by Rt. And of course, this will just be an algebraic space. But then again, I've got plenty of curves here that don't pass through P prime, that avoid any singular point. So I got plenty of Cartier divisors here that miss Q. And again, I can build a Neff divisor that avoids, Neff Cartier divisor that avoids Q. And then finally, observe that if I took an ample curve here, it has the property that it meets every curve on S prime. So I can build a curve which is Neff and meets every curve on T, and therefore it's ample by Nikai-Moitzesen. So then T prime is projective. Then the final thing to say is that if S and T are homeomorphic, then so are S prime and T prime, because they're just the quotient, both the quotient topology. Okay, so, and then because of observation number 1, I guess never erased it, if I can show that the S prime and T prime are isomorphic, then S and T are isomorphic. It's just a rational question. Okay. So therefore, I may assume that S is minimal. Okay, well, so then I apply the Kadara-Enriquez classification. Okay, so most of the time, S maps to another curve, C, with, there's a contraction morphism. And there are plenty of fibers. Okay, so then on T, I'd see lots of curves G, and G cover T, and they don't intersect each other. And so then if you, again, apply the Hodge index theorem, run the same sort of argument I ran up here. What that implies is that, I mean, they can't be, it's actually much easier, right? Because if they're disjoint, one of them has negative self-intersection, or they both have 0 intersection. They can't all have negative self-intersection. That's impossible because you can contract all of them, and you can't contract that many curves on the surface. And if they don't intersect, then they're all proportional. And then there's a theorem of Totaro that says if you have 3 such curves, they form a family. These form a family. Because again, after all, I've only got countably many curves. I'm only over a countable field. So, I mean, I don't otherwise know that they form a family. Sorry? I don't No, I've not thought about that. That would be nice. Well, I mean, to me that seems on the opaque side, but in the end it must be true, right? If they're isomorphic, then the cones and curves are the same. It seems the question is, can you tell the cones and curves are the same? I mean, I can't even tell at the moment, even if T was smooth, and I contracted on one side a -1 curve, I don't know that on the other side I contracted a -1 curve. I could have contracted a curve of genus 1,000,000, I mean, as far as I can see, at the moment. And then there's a slight argument to show that, for example, let's do the only real case I can do so far is a P1 bundle. Let's suppose that this guy is a P1 bundle, then it's not so hard, given the fact I have a family, that in fact I actually get a morphism. Okay, now you can't imagine how useful it is to have this morphism, because now you've got curves on one side that form a family, and then they correspond to curves on the other side that, in the same family. I mean, I don't know what the genus, I don't know how the genus of C and the genus D compare. I don't know how the genus of the fibers compare, but at least somehow I have something on both sides which is algebraic, which corresponds to my homeomorphism. Okay, so then that's the next thing. The next thing is to show that T is a P1 bundle. But in other words, the hard thing is to show that the fibers are rational. What's that? Oh, only, well, you'll see. Just have to be a little bit careful. Just because I have a family of curves, it could be, it's a Hilbert scheme argument, right? So, I mean, that family, it could be, some family here, right? But if I have a P1 bundle, I have a section, then I have lots of sections here, and it forces it to be a fibration. But yes, I mean, of course, I want to use the whole. Okay. Okay, so let's take a pencil of sections on S. So a whole bunch of nice P1 bundle, S, and a whole bunch of sections. Of course, a pencil, so they'll have some base locus. These are all basically arguments that appear in the paper by Kähler and his collaborators. But everything's much easier in this case because I actually have a fibration. Okay, so let's say these curves are CI. Again, this is only sort of countable in the end. But it's a nice algebraic family. So what do I see on T? Well, I see a whole bunch of curves DI that map 1-to-1 down to D. So at least I know this map is an isomorphism in characteristic 0. That's where I use characteristic 0 in a big way. And so, for example, I know that the genus of DI is equal to the genus of D. Okay. So if I could show this was an algebraic family, I could just use bend or break. Or just anything from the classification of surfaces, right? So the question is, why is this an algebraic family? Okay, well, so let's assume that so there are two cases. Number one, we have an elliptic fibration. I mean, by which I mean, I don't know that T is smooth, right? But by which I just mean that the general fibers, maybe just general fiber is genus 1. Or case number 2, which is a little bit harder, is the general fiber is genus 2. So in this case, I don't think this case can occur, though there's now he's having. I think this argument is okay. It was always before any talk I start having doubts. So I just look at the I look at my generic fiber, right? And that's basically a curve of genus 1. So these sections, well, actually it's an elliptic curve, right? I have plenty of sections, sorry. These sections, di, they basically correspond to, if I fix one of them, just orthomorphisms of the generic fiber, right? So that's simply transitive. So if I picked one fiber and one point of that fiber, I could certainly find a section, di, passing through that point. But then if I chose another fiber and forced di to pass through a different point of that fiber, I couldn't have an elliptic fibration. And I've got plenty of those curves here. So it seems to me that this is impossible. Okay, so what about this case? Well, I'm not a number theorist, but I suspect there's some sort of number theory argument here. But let me just give you a geometric argument. Essentially what that means, modulo some simple cases to eliminate, that T is general type. Well, so then I apply a junction. So I've got kt plus d dot di dot di. Well, that's k of di. So that's 2 genus d minus 2. So this is fixed. So we've already decided, same sort of argument, that there's no way that these curves can all have negative self-intersection, so throw away many of them. The rest have non-negative self-intersection. So what that tells me is that kt.di is bounded. But, if I'm on a variety of general type and I bound this, then that tells me that I have an algebraic family. And now once I have an algebraic family, bend and break tells me I have P1s and I have a P1 bundle. Okay. Let's see, I'm sort of running a little bit out of time. If it's a P1 bundle, there's still quite a bit of argument, but the first thing to sort of show is, again, that sections correspond to sections, and there's sort of some quite argument I quite like, but let me skip it. Okay, where are we? Okay, so now let me sort of point out where I'm stuck, and maybe where there's a way out. And then maybe end with some questions. So now, having dealt with the P1 bundle case. Oh, by the way, once you know lots of sections on one family correspond to sections on the other family, and you have a P1 bond, then basically you know it's birational to product. Then it's not so hard to finish. Again, it's kind of fiddly, but you know so much by that time, then it's not so hard to finish. So then the next case, of course, just going through the classification is S to C is an elliptic fibration. Well, again, I suppose that there might not be any sections. So let's just suppose there is a double section. We'll sort of come back to this issue. But suppose there's a double section, so then there are lots of double sections, right? Because that's basically because if you take 2 points in an elliptic curve, it moves in a pencil, right? So if you take a double section, add lots of fibers, you can move that guy in a lot of pencils. So then on T, you would see lots of double sections. Okay, but now sort of presumably, well, we don't know what we've got, right? We don't know if it's let's just write some vibration. And again, just let's assume it actually forms a family, and that's not really much of an issue. So you'd see a double section, so there'd be some ramification points. But what would be really annoying, and which I have no idea how to control at the moment, is that you could have singularities. I mean, you could have. I mean, all you know, right, is that these curves di, they map 2 to 1 to d. That's it. And then so in every fiber, there's either 2 points or 1 point. If there's 2 points, that's fine. That's just a locally an isomorphism. If it's a ramification point, that's fine. But what if it's not a ramification point, it's a singular point, and it's essentially just two smooth curves intersecting arbitrarily high. And again, you can't see the multiplicity, right? So in these arguments I've been trying to run, where I sort of argue that if T is of general type, then I just naively apply a junction, I'm stuck because the arithmetic genus is very high. But let me just observe one thing. At least the geometric genus, this guy is still bounded. So there's a very, very hard conjecture, much harder than this conjecture, that would basically say you'd be OK in this case if T was algebraically hyperbolic, then what that says is that there's a sort of, if you fix the genus, there's only a bounded family of curves on a surface of general type of that genus. And again, then algebraic families here would correspond, double sections here, which form an algebraic family, would correspond to double sections here. That's way too much to suppose, but it seems that it's at least going in the right direction. And of course, at the beginning, when I had these negative curves, I was thinking, well, if I bounded the self-intersection from below, then that's another conjecture which is true, but of course it's much easier than that. So let me say maybe end with one thing. So one question. So how easy is it to see finite Ital covers? Or more generally, just finite covers. So really specifically, I mean, given let's say an Ital cover of S, does that correspond to an Ital cover of T? I just don't have any idea about that. But if that was sort of true, then you'd really be in control, because then you'd have some control of the fundamental group of S, and you'd be able to talk about the genus. You could have control of the genus of C and the genus of D. And then, yeah, well, maybe I should just end there.